Welcome to the second screencast on nerves. This screencast deals with resting potential, action potential, and propagation of action potential. So dealing with the first slide here, which deals with resting potential. Resting potential is the voltage across the cell membrane of an excitable cell, in this case a neuron, at rest. Okay, and it is between about minus 60 and minus 70 millivolts, with the inside the cell being negative with respect to the outside. Okay, now if I deal with why that occurs, if I go down and look at this diagram here, this represents the cell surface membrane of one of these excitable cells. In this case, let's say it's an axon of let's say a motor neuron, but it could be any part of the cell membrane of either a sensory neuron or a motor neuron. Inside the fluid mosaic layer, or the phospholipid bilayer of the membrane, exists a thing called a sodium-potassium pump, which is a protein which acts as an active transporter, which uses ATP to extrude or pump out sodium ions from the inside of the cell. Okay, so this is the inside of the cell here, and that's the outside of the cell, and this pump here is pumping out sodium ions, and at the same time it pumps potassium ions in. Okay, so it's pumping potassium ions in and sodium ions out. In actual fact, there's an uneven distribution. It pumps 3 sodium ions out for every 2 potassium ions it pumps in. Okay, so that's called the sodium-potassium pump. Okay, and the uneven distribution, the fact that 3 positive charges go out to only every 2 goes in, immediately starts to produce an uneven distribution of positive charge, with more positive charge outside than inside. Okay, that difference is accentuated by the presence of these potassium ion channels, okay, which leak potassium ions out of the cell. Okay, so potassium ions are far more likely to leak out of the cell than sodium ions are likely to leak in. Okay, so sodium ions don't really leak in. In fact, the cell membrane is 20 times more permeable or leaky to potassium ions leaking out of the cell than sodium ions leaking in. Okay, added to that, we have in the cytoplasm of the neuron, or sometimes known as the axoplasm, if it's an axon we're talking about, we have proteins. Okay, so things like the proteins that make up the cytoskeleton of the axoplasm, and those tend to be negatively charged. Okay, so there's a degree of negative charge inside the cell which there isn't outside the cell, but there's also an awful lot more positive charge due to these sodium ions being pumped out of the cell, and also some of these potassium ions leaking out of the cell having already been pumped in. Okay, so that results in some positive charge outside the cell with respect to inside. Far more positive charge out here than inside. Okay, to the extent that there is about a charge of between minus 60 and 70 millivolts inside the cell with respect to being outside the cell in terms of a potential difference. Okay, so just looking back at my notes again, I want to pause the video here to take down some notes from these, and I'll quickly go through these. Okay, so we said resting potential is between about minus 60 millivolts and minus 17. The negative charge being inside the cell with respect to being positive outside. It's created by the sodium-potassium pump, which pumps out 3 sodium ions for every 2 potassium ions that it pumps in. But the potassium ions also leak out. The membrane is 20 times more permeable to potassium ions than sodium. Okay, so even though the potassium ions are pumped into the cell, they tend to leak back out again. Okay, as well as that, adding to that, we've got proteins in the cytoplasm or axoplasm of the neuron which are negatively charged. Okay, and so this word polarized, we say the cell is polarized. When it's at resting potential, we say it's polarized because it's got more positive charge outside than inside, and the potential difference or voltage across that cell is between minus 60 and minus 70 millivolts. Okay, And also, when the cell is polarised in this respect at resting potential, there are things called voltage-gated sodium ion channels, which we'll come across later, and they're very much closed. Okay, so the sodium ions cannot pass across the cell surface membrane. Okay, and that can be summarised by looking at a short animation below. Quickly look at this.
A nerve impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse.
Okay, so that deals with resting potential. If I now move on to look at the next slide, which deals with action potential. So this slide requires us to describe and explain how an action potential is generated. Okay. Now, if the cell is at resting potential as described on the previous slide, if the cell starts to depolarize due to some of this positive charge coming into the cell, and if it gets depolarized to minus 50 millivolts, remember at resting potential we were between minus 60 and minus 70 millivolts, if we manage to depolarize, I allow some positive charge in to reduce the voltage across the membrane to about minus 50 millivolts, what happens is that we reach something called threshold potential. Okay, and if threshold potential is reached, what happens is that ions in the cell surface membrane, which are called voltage-gated sodium ion channels, suddenly open. Okay, and when they suddenly open, what happens is that there is a large amount of sodium ions will be able to diffuse in through these voltage-gated ion channels. Okay, they open, the sodium ions diffuse in. So there's a sudden rush of sodium ions of this positive charge into the cell until the cell reaches about plus 40 millivolts, and that's described as action potential. Okay, so if you like, we start off at resting potential, and if there's some leakage of sodium ions into the cell, which allows the cell to reduce its potential across the membrane to this threshold potential of about minus 50 millivolts, what happens is voltage-gated ion channels open, okay, and then suddenly we reach about plus 40 millivolts, which is known as action potential. So we've gone from resting potential to threshold potential and suddenly to action potential. Okay, at this point we describe the cell as being depolarized, whilst at resting potential we can describe the cell membrane as being polarized. At action potential we say the cell membrane has been depolarized. Okay, and immediately after depolarization what happens is that sodium ion channels then shut. Okay, so they open for a while, allow sodium ions in, and then close. Okay, and at that point, plus 40 millivolts, what happens is that we have other proteins in the cell surface membrane which are called voltage-gated potassium ion channels, and they suddenly open, which allows potassium ions to diffuse out. Okay, and that movement of positive charge out of the cell causes the the cell surface membrane to be repolarized, i.e. for it to start to reach resting potential again. Okay, and that's known as repolarization, and it's because of the movement of positive charge out of the cell due to these potassium ions moving out. Okay, and following action potential reached, and then after repolarization occurs, what happens is that the sodium potassium pumps, okay, start to work again. Well, they've been working all the time, but they will start to restore the idea of resting potential with sodium ions on the outside of the cell, which returns the cell surface membrane to what's known as a resting potential. Okay, after the voltage gated ion channels have opened and shut, they remain inactive for a period of time when they can't be re-stimulated to open, irrespective of changes in voltage, and this is known as refractory period. Okay, and that's quite important for the transmission of a nerve impulse, and we'll come back and look at that later. Okay, looking at some diagrams of that, we have first of all, we have this diagram here where we're seeing the state of the various ion channels at resting potential, at depolarization and repolarization, and then resting potential again. Okay, so resting potential, as we dealt with in the last slide, we've got the sodium potassium pump here, pumping sodium ions out and potassium ions in. Okay, we have ion channels which are shut, okay, which don't allow voltage gated potassium ion channels, and voltage gated sodium ion channels don't allow the movement of potassium ions out or the sodium ions in. Okay, we then have depolarization, which occurs where we suddenly have sodium ion channels open, allowing sodium ions in, and that results in the inside the cell becoming more and more positively charged. Okay, until we reach something called action potential, which is up here. Okay, then we have potassium ion channels open, so the sodium ion channels shut, and now potassium ion channels open, allowing potassium ions out, which makes the cell more negatively charged. Because positive charge is leaving the cell, the inside the cell becomes more negatively charged. We call that repolarization. Okay, and then what happens is that resting potential here is achieved again by the activity of the sodium potassium pump there. Okay, hopefully that makes sense. And again, I've got this in a moving animation here. So what I've got here is resting potential, where I've got the green blobs represent the sodium ions, and the blue blobs represent the potassium ions. At resting potential, we've got lots more sodium ions outside the cell than inside the cell, and we've also got some potassium ions outside the cell because they've been able to leak out. Okay, so we've got resting potential there. Okay, and that's so what's happening here is that sodium ion, the sodium potassium pump is now pumping 3 sodium ions out for every 2 potassium ions in. Okay, you see that on the right there. I'll just play that again. So 3 sodium ions are being extruded or pumped out of the cell, and 2 potassium ions are going into the cell. Okay, so that's what happens there. And then here we have depolarization. Okay, so we've got a sodium ion channel that's opened, okay, and in rush the sodium ions. Okay, then what happens is that the sodium ion channels close, these voltage gated sodium ion channels close as the insides of the cells become more positively charged. Okay, and then what happens is the potassium ion channel opens, which allows potassium ions out, which causes the repolarization of the cell. Okay, so that's what happens there. And then the cell returns to resting by the activity of the sodium potassium pump again. whilst this animation is quite nice and simple, what it doesn't show, of course, is the potassium ions leaking out of the cell at resting potential, which is one of the major contributors to the fact that at rest the cell is more positively charged outside than inside. Okay, but it shows the voltage-gated ion channels and the voltage-gated sodium ion channels opening, and the voltage-gated potassium ion channels opening rather nicely, and the sodium-potassium pump in action rather nicely. Okay, so just summarising all of that, you might want to pause the screencast there to look at these notes to make sure that you are completely au fait with all these words in bold and what they mean. Threshold potential, arresting potential, voltage-gated sodium ion channels, action potential, depolarized voltage-gated potassium ion channels, refractory period, and sodium-potassium pumps. Okay, you need to know what all these words mean and be able to use those to describe not only how an action potential is generated, but also how resting potential is achieved. So moving to the next slide, the third slide here deals with how the action potential is transmitted along the length of an axon. So far we've looked in the first slide, we looked at resting potential, and then we looked how that resting potential becomes a thing called an action potential by the movement of sodium and potassium ions in and out of the nerve cell. Okay, so what we're going to now look at is what happens when all of these sodium ions diffuse into the nerve cell through voltage-gated sodium ion channels. Okay, the result of that is that the sodium ion concentration inside the cell, close to the sodium ion channel, increases, and that results in diffusion of the sodium ions away from the sodium ion channel, down concentration gradients. Okay, and we call that a local current. Okay, so diagrammatically, as the sodium ions diffuse in, what happens is that they diffuse laterally, sideways, okay, away from where they've diffused in, just along a concentration gradient. Okay, the result of this, what's known as a local current, or this charge moving here, is that the cell on an adjacent thing suddenly becomes more positively charged because of this lateral diffusion of positively charged sodium ions, and that causes a depolarization of this part of the membrane, which causes voltage-gated ion channels. Remember, these voltage-gated ion channels respond to change in voltage. Now, the movement of these positively charged sodium ions sideways changes the voltage in the adjacent part of the membrane, which opens the next set of voltage-gated ion channels, and the sodium ions rush in. Okay, so the whole process repeats itself, and it moves sequentially along. Okay, so this diagram here shows you what's happening in our axoplasm. These things represent the voltage-gated ion channels, these black things, and this graph here is the membrane potential and then distance along the axon. Okay, so at time equals 0, okay, we've got a depolarization occurring here. Okay, now a little bit further along, 1 millisecond later, what happens is that the whole thing is shifted to the right, whereby we now have the depolarization happening here. Okay, so our action potential has moved, okay, along to the next bit of the membrane. Okay, and then that continues along. If we move this down to 2 milliseconds, again, what we can see is now the action potential has moved along, further along the axon. Okay, and the voltage-gated ion channels are opening further along the axon. The reason that it doesn't move back on itself, the reason that these, once this has been depolarized here, the reason that these voltage-gated ion channels don't open again is because once these voltage-gated ion channels open, they then close, and they remain closed for a period of time before they can be reopened. Okay, and that's very important because it ensures that the impulse, the nerve impulse, only moves in one direction. Okay, it can't move back on itself. Okay, so let's say it starts here, it can only move in that direction. Okay, it can't start moving along there and then start moving back on itself because of this idea of refractory period. Okay, now if it starts in one particular area, obviously it can go around in both directions. Okay, so it would move around the whole nerve fibre. Okay, along both sides or both bits of the axon. Okay, so that's one of the reasons that nerve impulses can only move in one direction, which is very important. Okay, if I can summarise that in a little animation here.
An action potential, depicted as a red band, is propagated in one direction along the axon. During an action potential, the inside of the cell membrane becomes positive with respect to the outside. An action potential generates local currents that tend to depolarize the membrane immediately adjacent to the action potential. When depolarization caused by the local currents reaches threshold, a new action potential is produced adjacent to the original one. Action potential propagation occurs in one direction because the recently depolarized area of the membrane is in absolute refractory period and cannot generate an action potential.
Moving back here, the second half of this slide deals with myelinated axons. Remember when we looked at the structure of nerve fibres, we talked about things called Schwann cells, which are cells which are wrapped around the axon, which insulate the axon from neighbouring cells. But what they're also involved in is speeding up the rate at which this impulse moves along an axon. Okay, so the fatty material, myelin, okay, we describe as a myelinated axon, is due to this fatty material and these Schwann cells. Okay, as we looked at in the last screencast on structure of nerve cells. Okay, now I mentioned things called nodes of Ranvier when we looked at the structure of the cell. These are little gaps between Schwann cells, and what happens is that as the action potential is propagated along an axon, what happens is that the voltage-gated ion channels only open where the nodes of Ranvier happen. Okay, because the voltage-gated ion channels don't exist underneath the actual Schwann cell, and even if they did, that part of the cell is insulated, so sodium ions can't pass through the cell surface membrane because of this Schwann cell that's wrapped around the axon at that point. Okay, so it's only at the gaps between Schwann cells that all this occurs. Okay, so only the changes in ion permeability in the membrane only occurs at the nodes of Ranvier. Okay, the advantage of this is it dramatically speeds up the propagation of an action potential along an axon. Okay, and that's known as something called saltatory conduction, saltatory to jump. Okay, so the action potential jumps from node to node as we move along, representing that diagrammatically down here. I've got a diagram which shows my action potential being achieved here, okay, and then the local current, those sodium ions diffusing right across the length of this Schwann cell here and causing a depolarization at the next node of Ranvier, and then it jumps to the next one. Okay, so it jumps from here to here to here rather than moving all the way along the membrane, and that makes the impulse move more rapidly along the axon. Okay, so that's known as saltatory conduction. Okay, and occurs in what we call myelinated neurons, which have these Schwann cells which are separated by gaps which are called nodes of Ranvier. All of these words are words that you should know. So I can just pause the screencast, or if you can pause the screencast there for a second, you can pick up some of these key words like local current, propagation of action potential, Schwann cell, node of Ranvier, saltatory conduction, you should understand what all these terms mean. So moving on to the next slide. This slide reiterates some of the things I've already mentioned. The slide requires you to interpret graphs of voltage changes taking place during the generation and transmission of action potential. Okay, so let's deal with the generation of action potential first of all. Okay, and I've shown you one of these graphs already. Okay, so this is what a graph of action potential. So we've got a membrane potential with respect to time here at a particular point on an axon membrane. So what happens is that at resting potential, which is about, let's say, minus 65 millivolts, what happens is that there could be a stimulus which causes a leakage of sodium ions, and once we reach a point of, let's say, minus 55 or minus 50 millivolts, which we call resting potential, what happens is that these voltage-gated sodium ion channels open, sodium ions rush in, and the inside of the cell becomes much more positively charged until it reaches about plus 40 millivolts, which is termed action potential. Okay, so resting potential is about minus 65. We then might have threshold potential, which let's say might be minus 55, and then we've got action potential, which is about plus 40. Okay, then what happens is that the inside the cell starts to become negatively charged. The reason for that happening is due to these voltage-gated potassium ion channels opening, which allows potassium ions to start diffusing out. Okay, and that's called repolarization. Okay, and remember, we then have a period after repolarization, okay, called refractory period, which is when the sodium gates can't open. Okay, so they remain shut for a period of time, okay, where they can't be re-stimulated to open, and we call that refractory period. Okay, and during that time, resting potential is achieved again by the activity of the sodium-potassium pumps. Okay, and so that deals with voltage-gated changes taking place during the generation of an action potential. Now, graphs involving the transmission or propagation, I tend to call it transmission of an action potential. I've shown you these graphs before, but I'll quickly go through them again. Okay, this shows you a graph here of membrane potential with respect to the distance along the axon, okay, and at various times, time equals 0, time equals 1 millisecond, and time equals 2 milliseconds. We'll have a look at in a second. Okay, so in terms of how to interpret this, is obviously we've got action potential being reached here at 2 millimeters along our axon, okay, at time equals 0. Okay, so that's our action potential here. Okay, but then the next graph looks at what happens at 1 millisecond later, and we can see that 1 millisecond later the action potential has moved to 3 millimeters along our axon. Okay, and then the whole pattern continues, whereby here at 2 milliseconds the action potential is now at 4 millimeters. Okay, so that shows you how to interpret graphs of the transmission of an action potential. Okay, so that's the second series of graphs deals with transmission of an action potential, whereas the first graph here deals with generation of an action potential. Okay, and moving on to the next slide. This slide requires us to outline the significance of the frequency of impulse transmission. Now, what does all of that mean? From what we've seen so far, an action potential either happens or it doesn't. Okay, and this is called the all or nothing law. Okay, so when a stimulus happens on a piece of membrane of a neuron, okay, threshold potential is reached, and if it does, we get an action potential. Okay, so threshold potential will lead to action potential. If threshold potential isn't reached, nothing happens at all. Okay, so the idea of all, okay, all being an action potential being reached, or nothing. Okay, so the size of the action potential cannot convey any sense of the intensity of a stimulus. Okay, because there's either an action potential or there isn't. Okay, there isn't the idea of different sized action potentials to transmit any information about the intensity of any form of stimulus. Okay, so as I say here, the action potential is a set value. Okay, it's always about plus 40 millivolts. Okay, so it can't communicate any information about intensity of stimulus. Okay, so how does the nervous system convey information about the intensity of stimulus? The answer is that a high intensity of stimulus, that creates more depolarizations, okay, which leads to a higher frequency of impulses. Okay, so an impulse gets sent along, and then if the stimulus was great, i.e. lots of depolarization occurred, what would happen is that once the nerve impulse had gone through a refractory period, what would happen is another impulse would be sent along. Okay, and the frequency of these impulses being sent along an axon conveys information about the intensity of the stimulus. Okay, and so it is therefore frequency of nerve impulses that provides information about the intensity of the stimulus. Okay, and if we look at this here, this little animation demonstrates that rather nicely.
The role of a neuron is to receive and transmit information. Neurons receive information with the dendrite. The dendrite receives information either from a junction with another neuron called a synapse, or the dendrite may be differentiated as a sense receptor to detect specific sensory stimuli, such as chemicals for taste and smell, pressure or heat for hearing and touch, or wavelengths of light for vision. If the dendrite is a sensory receptor, it responds to the intensity of the sensory stimulus. In the case of taste and smell, it is the amount of the chemical. For hearing or touch, it is the loudness of the sound or the heat or pressure on the skin. And for vision, it is the brightness of the light. The intensity of the stimulus produces a proportional electrical depolarization or reversal of charge in the dendrite. This graded depolarization is called the receptor potential. If the stimulus intensity is too weak, the receptor potential dies out before it reaches the axon cone, and the neuron does not convey any information about the stimulus. However, if the stimulus intensity is sufficiently strong to cause a receptor potential that reaches the axon cone, it will generate action potentials in the axon. Action potentials are all or none responses, so they are not proportional to the intensity of the stimulus. The more intense the stimulus, the greater the receptor potential in the dendrite, and the higher the frequency of the action potentials in the axon. A low-intensity stimulus causes a weak receptor potential and a low frequency of action potentials. A moderate-intensity stimulus causes a stronger receptor potential and a higher frequency of action potentials. And finally, a strong stimulus produces a large receptor potential and a high frequency of action potentials in the axon. In the previous scene, we described the covering of the axon by the Schwann cells. Here we shall explain what that means functionally. Schwann cells enclose the axon surface of vertebrate neurons in a tight myelin sheath. The myelin sheath of vertebrate neurons is not continuous and is interrupted at intervals with gaps called the nodes of Ranvier. Action potentials are not conducted along the axonal membrane that is covered by the myelin sheath. Rather, action potentials progress along the axon by saltation or jumping between the nodes of Ranvier. The action potential at one node induces an electrical depolarization in the exposed excitable axon membrane of the next node, which causes the action potential to appear at that node, and so on down the axon. By contrast, the loose continuous tunication of invertebrate axons by Schwann cells does not block the action potential, and the action potential progresses along the entire membrane surface of the axon. Myelination means that action potentials travel along axons more rapidly in vertebrate neurons as compared to tunicated invertebrate neurons. We will now examine how information is conveyed through the nervous system.
This last slide looks reiterates what we've already said on a number of the other slides, but it says compare and contrast the structure and function of myelinated and non-myelinated neurons. Okay, so I won't go through the myelinated one any further than I've already done, because it's covering things we've already talked about, things like Schwann cells, nodes of RAM-VA, and the idea of saltatory conduction. Okay, so we talked about that. Just looking at non-myelinated fibres, okay, what happens is that they tend to have Schwann cells as well, but we tend to have a number of axons embedded within the same Schwann cell. They don't have the idea of the nodes of RAM-VA, and the myelin in the which is involved in these Schwann cells is purely there as an electrical insulator, okay, which prevents electrical activity or an impulse in one nerve fibre interfering with any activity in any adjacent axons. Okay, so that's what happens in a non-myelinated fibre. So they don't have the nodes of RAM-VA, and they don't have the adaptation for rapid transmission of an action potential in the way that a myelinated neuron does. Okay, and in this case the action potential travels along the whole length of the axon, which is much slower than in saltatory conduction. Okay, if I most of this slide is involved with quite a lengthy animation, but I put it there because it covers quite a lot of the ideas that we've covered in this whole screencast.
What you will see and hear in this presentation is the development of myelin in the peripheral nervous system and the propagation of the action potential along a myelinated axon. This multimedia presentation will be most helpful if you already have a good understanding of the Schwann cell and the electrochemical process of the neuron, called the action potential. The Schwann cell forms a protective covering around the axon. Schwann cells start to develop in the embryo and continue to increase the wrapping around the axon through childhood. This development increases the thickness of the wrappings, which peaks in adolescence. This is why teenagers have such quick responses. The Schwann cell contains the typical cell organelles and cell membrane structure. However, notice as the Schwann cell surrounds the axon that the nucleus and other organelles are squeezed to the outside wrapping of the cell. This outer wrapping of the Schwann cell is called the njlm. The inner lining is made up of layers upon layers of cell membrane. This inner wrapping is called the myelin sheath. You will recall that the cell membrane, called the fluid mosaic model, is made up of a bilayer of lipids integrated with proteins. The thicker the myelin, in other words, the more layers of cell membrane making up the myelin, the more advantageous it is to the axon. One advantage is the regeneration of severed axons. Another advantage is an increase in the speed of the propagation of the action potential along the axon. The rest of this presentation will concentrate on the increased speed of action potentials down the length of the myelinated axon. Here is the neuron, and you can see the repeated Schwann cell membrane forming the myelin. Note that there is a small space between the Schwann cells where the axon is not covered by the neuroglial cell. These spaces are called nodes of RAM-VA. From what you already know, action potentials occur at the axon hillock and continue to be repeated away from the cell body, much like dominoes falling one after another. An action potential starts on a polarized membrane, which is -70. A stimulus causes the sodium gates to open slightly, and sodium starts to trickle into the cell. If the cell reaches -60 or threshold, the sodium gates open wide and sodium floods in, bringing the inside of the axon to +30. At this point, the sodium gates close and potassium gates open. Potassium starts to pour out of the cell. This allows the neuron to become polarized again. Then the sodium-potassium pump starts to actively transport sodium out and potassium back into the neuron. First, we will look at the propagation of the action potential in the unmyelinated axon. Propagation is the repeating of action potentials down the axon. The action potential is repeated because as the sodium comes in, it diffuses to adjacent areas within the axon. As the sodium increases in this area, threshold is reached. Sodium gates open wide, sodium rushes in, causing depolarization and an action potential. As the sodium enters this area, it diffuses through the axoplasm and another action potential is created. This continues down the length of the axon. Now look at the myelinated axon. The same process applies to the myelinated axon. An action potential develops, and as the sodium comes in, it diffuses through the cytoplasm of the axon. It continues to diffuse through the portion of the axon wrapped in myelin. The increased sodium concentration reaches the node of Ranvier, increases the axoplasm to -60, and depolarization occurs. The sodium gates open wide, sodium floods in, and we have an action potential. Again, the sodiums diffuse through the axoplasm, reaching the next node. An action potential develops. The process is continued down the myelinated axon, passing from node to node. Compare the unmyelinated axon with the myelinated axon. You can see that action potential reached the end of the myelinated axon more rapidly than the unmyelinated axon. The speed of the propagation is faster going from node to node than action potentials that develop adjacent to the previous action potential.
This concludes our look at the screencast on resting potentials, threshold potentials, action potentials, and transmission of action potentials along axons, and the difference between myelinated and non-myelinated neurons.